In this lecture, we're going to talk about time series forecasting. And time series forecasting essentially is again predictive modeling, right? You're trying to predict what's going to happen in the future, but you're essentially using time as a proxy. You're not going to look at causal variables, causation, but you're just going to look at time. You're assuming that the past kind of repeats itself, and so you're just going to focus on time as the dependent variable to predict the future. So time series is a set of observations on a quantitative variable collected over time. Example, Dow Jones Industrial Average, historical data on sales, inventory, customer counts, interest rates, costs, etc. Businesses are often interested in forecasting time series variables, and often independent variables are not available to build a regression model but when you have the time series. Time series analysis, we analyze the past behavior of a variable in order to predict its future behavior. So some time series terms are stationary data. Here we are looking at time series where data does not exhibit significant upward or downward trend. And if you look at the diagram, we see some fluctuations of data, but pretty much it's flat, and this is stationary. Non-stationary data is basically time series variable exhibiting significant upward or downward trend over a period of time. And if I want to draw this out, your non-stationary data would be, here is a positive trend, and here is one with negative trend. Basically here is time, the x-axis, and this is your sales data or revenue or cost or whatever it is that you are trying to predict. And the last one, which we're going to look at, is seasonal data, time series variable exhibiting repeated patterns at regular intervals. And if I was going to draw this out, again, you have x-axis is time, y-axis is what you're trying to predict. And let's assume that, let's say we're looking at, this is the year one, we have 4 quarters, year 2, we have 4 quarters. And maybe we're looking at summer sales. It drops again, increases in the summer, drops during the winter. So essentially what we're looking at here is maybe bikini sales or swimwear, and it peaks right here. Or if you're looking at skiing, it'd probably be the opposite. And this is seasonal variations, which you can take into account. There are many different techniques for time series techniques, and it's impossible to know which technique is suitable for a particular set of data. It's customary to try out different techniques, select the one that seems to work best. And to be an effective time series modeler, you need to keep several time series techniques in your toolbox. And how do we measure the accuracy? There are different ways we can use to measure the accuracy of time series data. 4 common techniques which we're going to look at is mean absolute deviation. Mean absolute deviation, we take the actual data, yi is your actual values, y hat I is your forecasted data. We take the difference, and the difference between actual minus forecast gives you error. We take the absolute value of error, and we find the average of these absolute values, right? Which essentially gives you the mean absolute deviation. So essentially this is your average distance from the actual value. Your forecast minus the actual is your distance, and when you take the absolute distance, this is the average distance of that. The second one is mean absolute percentage error, right? So we take the actual value, this is the actual value, yi, this is your forecast, so this is your absolute error, and you divide it by the actual value, so this is percentage error, and you take the average of that to get mean absolute percentage error. And then you have mean squared error. Mean squared error gives you the squared distance from your mean. Okay, and if you take the square root of this, the square root of this would give you root mean squared error, which also gives you the average distance from your mean. We take each value, actual value subtracted from its forecast, we square that, and we take the average of all these squares. And talk about root mean squared error, which is square root of mean squared error. And we will, in this thing, focus on mean squared error or root mean squared error because that gives you a better idea of what the value means. Extrapolation models that try to account for past behavior of a time series variable in an effort to predict future variable. Essentially, we are looking at the past. Your yt is your current actual value. Yt minus 1 is previous time period, 2 time periods ago. And this is your prediction for the next time period. And we're going to talk about several extrapolation techniques that are appropriate for stationary data. So first step is we're going to talk about stationary data. Let's take an example. Electricity is a retail store that sells audio and video equipment for home and car. Each month, the manager of the store must order merchandise from a distant warehouse. Currently, the manager is trying to estimate how many VCRs the store is likely to sell in the next month. He's collected 24 months of data, and I'm just going to open up the Excel file. And you can see here's your time period and number of VCRs sold. And the best way to look at this data, visualize this data, is to actually build a scatter plot. You can use scatter with only markers, or you can use with lines with markers. And here is an example of a scatter plot. I'm just going to select this here, insert, scatter. There we go. So gets an idea of how your data, and you can see it's pretty flat. There's ups and downs, which could be due to error, but it's pretty flat. So the first and the most simplest method is called moving averages. And you see this function here, the prediction of, we're talking about yt plus 1, where t is your time period, right? So let's say we are trying to predict for period number 3, then t plus 1 is equal to 3, therefore t is equal to 2, okay? And k here is how many periods moving average are we going to take? So maybe k is equal to 2, which means we're looking at 2 period moving average. Okay, we're looking at a 2 period moving average. So going back here, we're looking at y hat 3 is going to be equal to y2 plus y1 divided by 2. We take the previous periods, 2 periods actual, and then we divide it by number of periods we're going to take. Let's take an example where we're going to look at y hat 6, and let's say here k is a 4 period moving average. We would look at y5 plus y4 plus y3 plus y2, last 4 periods, and we take the average and we use that as a prediction. So there's no general method exists for determining k. We try out several values of k and see what works best. The more number of periods you take, if k is larger, the flatter your forecast is going to be. It does not take into account the fluctuations. The smaller time periods you take, the more you're going to take account. So let's look at implementing the model. And here we have an example of a 2 period moving average. We leave the first 2 periods blank and we calculate its moving average. Essentially, I'm just going to go ahead and delete this for the time being so we can rework this. So We have average. I'm going to select these two time periods. And I'm going to copy it right up to this point, which is fine. Now the forecast for the next time period, we can calculate the next time period, which is not a problem. But once we go down below the next time period, your forecast starts kind of deteriorating because you don't really have true pictures. So if you want to get the average to here, you'd have to select this and this. And since time period 25 is already a forecast, you're just adding the error, compounding the error further. And here you're going to essentially get the average of the previous two time periods. And so these forecasts are extremely suspect. Here you have these forecasts are very much suspect. These are not true forecasts. This would be your best forecast. The mean squared error, you could take each value, subtract it from its mean, and then find the average, square it, and then find the average, or you can use this function. The function we're going to use is called sum x m y 2, essentially sum of x minus y squared. And we're going to select your first row, first column, and the second column. Now this gives you the sum of the difference between the sum of the squares, and you got to then divide it by the number of items you have to get the average. And that's 6.93 here. Okay. The square root of this value is root mean squared error. So that would be the square root of that. Similarly, if you're going to use a 4-period moving average, I would leave the first 4 periods free and start off with the 5th period. And I would develop the average based on that, the previous 4 periods. And I'm going to copy this right down up to here. And then here, it would be the same formula. I would select the 4 time periods. That's perfect. But starting with the next time period, time period 26, I would have to start picking the last 3 and then a forecast. And here would be last 2 and then the forecast here. The last one would be, you have only one true value and the other ones are all forecast. So these are suspect values. So these are all tainted by using forecast. And again, your root mean squared error is 7.66, and sorry, your mean square error is 7.66, your root mean square is 2.77. Essentially what we are saying here is this 2.63 is this forecast on average is going to be off. The predicted value is going to be off by 2.63 VCR. Since we are looking at VCRs, we are saying it's going to be off by 2.63 VCRs. So this is your simplest and the easiest forecasting method, which is moving average, simple moving average. So when you're comparing mean squared errors, you should take care when comparing mean squared error values from different forecasts. The lowest mean squared error may result from a technique that fits the older values very well but fits recent values poorly. This may be because the situation has changed and the past is no longer repeating itself. It is wise to compute mean squared errors for only most recent values. And we looked at how to calculate the forecast for time periods 25 and 26. And you notice that for time period 26, you're actually using the forecasted value, which would cause it to be tainted. The second method which we are going to look at, and these are static methods, what we call static methods, is called weighted moving average. The moving average techniques assigns, the simple moving average assigns equal weights to all previous observations, whereas the weighted moving average actually tries to assign different weights. So the simple weights is just essentially 1 by k. In weighted moving average techniques, it allows us to assign different weights to previous observations, and the sum of all these weights should be equal to 100%, and each weight is between 0 and 1. And ideally, we need to determine values for your weights, and we can actually do that using our solver. So let's look at this model. Here's the weighted moving average. So we're going to look at a 2-month weighted moving average, and I'm going to start off with the weights being equal. This is your simple moving average. You notice that in simple moving average we had 6.93, and in weighted moving average we get the same mean squared error. And so the way it goes is that if you look at this, this is 2 periods. You have the 2 weights. Sum of that should be equal to 1. And we are saying W2. So we have W1 minus your previous time period plus W2 times the time period before. So each weight is essentially talks about how many time periods it goes behind by. So W1 is 1 time period, so it's 38 multiplied by W1 plus 33 multiplied by W2. So please make sure that you do that correctly. A lot of you in your exams kind of put W1 times your first time period plus W2 times your second time period. Please don't do that. It's kind of backwards from the time you want to forecast, okay? So make sure you do that. And once you get this, once you set this up and put all the weights, if let's say I asked you for a 4-period moving average, you can start off with 0.25, 0.25, 0.25, 0.25. And then what you have to do is we are trying to minimize our mean squared error. So we go up here, we set an objective which says our F7, we're trying to minimize the mean squared error by changing our variables. Our variables are these 2 variables. You can click plus, and that will essentially put your variables here. Your constraints are that the sum of these 2 variables should be equal to 1. And of course, these values are less than or equal to 1 and greater than or equal to 0. And once you have this, you can run it just like you did in your linear programming. Now this is non-linear, and you notice that it's taking your weight 1 is 29.1% and weight 2 is 70.9%. So essentially what we are saying is that we're going to select 29.1% of the previous time period and 70.86% of two time periods behind to form our new weighted moving average. And that makes sense if you actually look at the number of VCRs sold. It goes up, then comes down, then goes up, then comes down, then goes up, then comes down. Essentially 2 time periods ahead. Let's take an example. So if I'm looking at period number 5, this is more like period number 3 and period number 1 than it is like period number 2 and period number 4. So obviously that's why your weight 1 is less than weight 2 is a lot more. Okay? And this is your weighted moving average. And here is the answer. We looked at your, we have to calculate our forecasts for the time periods 25 and 26. So if you go back to the Excel file, of course, for time period 25, you're going to use the previous 2 values. For 26, you start using values of the forecast, and then 27 and 28, of course, you're using your actually forecasted values. So obviously, the last 3 are all tainted, and this is the only real forecast you're going to get. And this is your weighted moving average model, the next stationary model. The last stationary model we are going to discuss is exponential smoothing. And for exponential smoothing, we're introducing a new term, which is called alpha. And alpha is called it's called a learning parameter, learning constant, or adjustment parameter factor. Okay, and what is essentially a value between 0 and 1. And what we're going to say is, if you notice this here it takes your previous forecast, right? Exponential is using forecast for the next month or next time period, whatever the time period is, current forecast plus some percentage of the error. You notice this is nothing but your error, difference between your actual value and your forecast. And so it's some percentage of your error. So if your error is positive, let's say your alpha is 30%. You essentially are, if let's say you have forecasted less than your actual, then obviously the error is positive, and so your current forecast gets adjusted by 30% of your error. So it actually, next forecast for next month, it'll be more. However, if you have forecasted more than what you should have had, it takes that error and then reduces it by 30%. Okay? So this is what exponential smoothing does. So we have here, we can expand this equation. And so here is an example of exponential smoothing functions. The larger alpha is, the more, as you can see here, the larger alpha is, the more the data starts following your actuals. As you can see here, it's actually just following your actuals. And the closer it is to 0, the more smoother the data is. So we can look at implementation of the model. So let's go and take a look at the Excel file. So here we're going to look at the Excel file for exponential smoothing. And it's customary to set the first prediction value equal to the actual value. So you can just go ahead and put this equal to the actual value. You're going to have a variable called alpha. You can start off at 0.5. That's kind of normal to start off. And then you're going to implement the formula. The formula says this is going to be, your forecast is going to be the previous period's forecast plus alpha, right? Multiplied by your predicted value minus your actual value. So go ahead and do that. Don't forget to put a $sign before the alpha, because if you copy this down, it's going to create errors. And then you just copy this whole thing down up to this point. Your period number 25 is also going to be the same formula. You can copy it down. For period number 26, you're going to just use the previous time period. So period number 26 is nothing but your forecasted value. So the forecast becomes static for exponential smoothing because you don't have any data here. Okay? And so this is your exponential smoothing. You then have to modify your alpha. You want to minimize your mean squared error. So your mean squared error is right here. You can calculate your root mean squared error by taking the square root of this value. And you minimize your mean squared error by changing your alpha value. That's your decision variable. And alpha is less than or equal to 1 and greater than or equal to 0. You run it. Excel will search for the value which gives you the lowest mean squared error. And in this case, it comes to 0.268. Okay? And you're done with your exponential smoothing. With this, we finish our stationary forecasting model. We looked at 3 stationary forecasting models. And in the next file, this is what we saw. We saw looked at the predicted values. And in the next lecture, we're going to look at forecasting methods with seasonality.